Welcome to the Crazy Hat Chemist. So here we go again, another video on chemical kinetics. Bam! So today we're talking about rates and the rate law. Okay, so a rate law, otherwise known as rate equation, is the change in concentration of the reactants or the reactant per unit change in time. And that unit change in time could be seconds, milliseconds, minutes, hours, days, a variety of different units of time. Okay, so here is our rate equation or our rate law. Okay, R is for the rate. Okay, and it's always in terms of the reactants, never the products. Those brackets mean concentration. Okay, that's usually moles per liter. Okay, and this is the denominator is a change in time. Notice this negative sign is letting you know that the reactants are decreasing over time, and that should make sense because the reactants are on the left-hand side. Okay, that's what you're starting off with, and over time you're producing products. You're increasing the concentration of products, but the reactants are decreasing over time. So that's why that negative sign is there in the front to let you know that it's a decrease in the reactants. Okay, here's a generic equation. You got AA plus BB gives me XX. The lowercase letters are the stoichiometric coefficients. The capital letters are going to be formulas. The C over the arrow is going to be a catalyst. So let's discover this reaction just a little bit more, a generic reaction. So that C right there is a catalyst. Okay, and here is a rate law or a rate equation. Okay, rate laws are always with regards to the reactants and never the products. And that's why you see the A, the B, the C, which is a catalyst, and that's okay, but not the X. The X is not involved in a rate law or a rate equation because it is not a reactant. Okay, this is the rate is for the R. The rate constant is K. So the rate constant here is independent of concentration, but it is temperature dependent. So typically when given a rate constant, you'll be given the temperature value as well as just the rate constant value itself. If you change the temperature, then the rate constant changes. Okay? And we're going to discuss more of the rate constant and the temperature dependency of the rate constant in another unit on thermodynamics in the future. So hold on to that idea. Okay? This is the reaction order. So those superscript letters there of M, N, and P in this case are the reaction order. And these can be the following numbers here. 0, 1, 2, which represent zero order, first order, and second order. They can also be fractions and they can also be negative values. But here in this unit here of chemistry, I'm just going to be discussing zero order, first order, and second order rate laws. That's what we're going to be discussing here. In future years of chemistry, you'll be discussing the fractions and the negative values, but that's much, much more in the future. Okay? These reaction orders are not necessarily the stoichiometric coefficients from the balanced equation. And so that's why it's the M, N, and P and not the little lowercase a or the lowercase b on that balanced equation that was right there. Because they're not necessarily the stoichiometric coefficients. There is a special case of when that is, but those are mechanisms. And these reaction orders must be determined by experiment and experiment only. And that's what we're going to be spending a lot of time in this unit is analyzing experiments to determine the rate law from the data. Okay? And I am the Crazy Hat Chemist. That was another Crazy Hat video here, and I got a perfect pumpkin hat here for you today. Okay? It's like the top of a pumpkin. You can't beat that. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. And I am the Crazy Hat Chemist, and I'm going to see you next time for more chemistry videos and chemical kinetics. Bye for now.